This lesson is on how matter behaves in electric fields. And we'll really just discuss mostly applications here. The main things that we care to learn are how matter behaves, in particular how dipoles, conductors, insulators will behave in electric fields, and to understand what kinds of applications these have. Here's one example of silver strands on a very microscopic scale here, only about 30 microns, only 30 microns for this bar, behave under the influence of an electric field that's increasing in strength. So when the electric field is weak, the silver strands are jumbled up, but as the electric field increases from panel A to B to C to D, you can see how the orderliness of the silver strands improves. So this is then of interest when you want to deposit small strands of conducting material, say on electronic chips. So to understand how matter behaves in an electric field, we know that we're dealing with the electric force. The force on a particle is the charge times the strength of the electric field. And the electric force behaves just like any other force and based on Newton's second law. So then the acceleration of a particle is the ratio of the force to the mass of the particle. And in the case of the electric force, this is Q over m, the charge over the mass of the particle times the strength of the electric field. This particular ratio, the charge to mass, then will determine how the particle will behave in an electric field. So if the electric field is constant, the force is constant, and then the situation is fairly easy to resolve. If the electric field is variable with time, things get a little bit more complicated, but then if we have certain situations of symmetry, it may still be able to solve these relatively easily. So let's take an example of another application of charged particles in an electric field. So this is now electronic ink, and what happens is that you can have white or black pigment charged with opposite charges. So then when you apply different kinds of charge on the surfaces of the electronic ink tablet on one or the other surface, you can actually get white or black deposited on either surface. And this is what you have inside of your electronic reader, such as an Amazon Kindle, for example. The advantage of electronic ink, several advantages. You can actually get very high resolution in whatever you're showing on the screen. Another advantage is that actually there's no backlighting at all, so it consumes very low power, and also it's very easy on the eyes. Well, that was the main advantage that I want to point out. No power, no requirement for power, and also no backlighting, so it's easy on the eyes, and also the high resolution. So another example, which I'll solve in a separate problem, is this of a particle entering an electric field, and this is actually what we have in inkjet situation that occurs in inkjet printers. An example that we have already seen is how dipoles behave in electric fields. So when there's no electric field applied, the dipoles molecules are oriented every which way. But when there's an electric field applied, they'll line up along the electric field, and then when you change the electric field direction, they switch as well. And this is what you have in, for example, liquid crystal display on your calculator. So normal matter contains huge numbers of electrons. And it's, in fact, this constituency of matter that determines how interactions in chemistry and biology will take place on small scales. When we discuss the behavior of matter in electric fields, we distinguish between three basic types of matter: conducting matter, insulating matter, or semiconductors. You know that conductors are metallic, and they are made up of nuclei that have some electrons that are free to move within the metal. So then when we apply an electric field to this piece of metal, the electrons can move freely through it, and that creates a current, as we'll see later in the course. Protons themselves also experience the same electric force, but because they're fixed to the metal structure, they're not really free to move. Here's an interesting bit about conductors, something that we've actually already encountered in one of the experiments that we referenced earlier. If we put a conductor in a region that has no electric field, and then we charge it, so we give it extra charge, these extra charges, be they negative or positive, will repel each other to an equilibrium point where they'll actually be as far as possible from each other. So then, as a result, the electrons, say if it's negatively charged on a conductor, when the conductor is in equilibrium, will reside all on its surface. And we have already seen an example of this when we had a uncharged metal ball that was initially on which we induced opposite charges on either side with a negatively charged rod. Then we channeled the negative charge into the ground and removed the rod. At the end, the remnant positive charge excess is evenly distributed around the surface of the ball. Insulators have opposite properties to conductors in the sense that the electrons are not free to move in insulators, but they're tightly bound to their home atoms. So as a result of this, insulators in fact prohibit the carrying of current. If the molecules within the insulator have a dipole moment, if they behave like dipoles, they'll still orient themselves under the influence of an external electric field, and that will then change the electric field inside the insulator. And we'll talk about this later on in this course. And finally, semiconductors, such as silicon, are similar to insulators in the sense that the electrons are more or less bound to their home atoms. However, the degree to which an electron is bound to this home atom can change under the influence of heat. So if we heat up the semiconductor, we can actually give the electrons enough thermal energy to escape the home atom and to increase its conductivity. Or if you apply a strong electric field, we can also give the electrons enough, we can also drop the potential barrier for the electrons to leave the home atom and again increase the conductivity of the semiconductor. And we're familiar with semiconductors in computer chips, cameras, and so forth. Here's an example of a very basic semiconductor element called a MOSFET, a metal oxide semiconductor field effect transistor. And this is the kind of stuff that's present in very large numbers in microchips and computer processors and cell phones. So this is the summary that I had for the behavior of matter in electric fields, and I have only selected a few more practice problems at the end of the chapter for your preparation.